We now see example 17 in the section which is dealing with basis and dimension. Here we can see a vector space Fn over F, or otherwise we can say it as Rn over R. That means the field is F here. Okay. We are claiming that the dimension of Fn over F is n. For that, just think about the standard basis of n tuples. The first element in the basis will be the n tuple 1, 0, 0, 0, 0, etc. 0. The second will be 0, the n tuple 0, 1, 0, 0, etc. 0, etc. And the n tuple will be 0, 0, 0, etc. 1. So there will be n elements in this set, and that will say that Fn over F has a basis of elements n. That means the dimension will be n. Similarly, considering the set of all metric spaces of order m by n over the field F, now you can think likewise. The first matrix, the first entry will be 1, the rest will be zeros. Then the second entry will be 1 and the rest zeros, and so on. So how many such entries are there? Mn entries are there. So that means the number of elements in that basis will be Mn. So the dimension of Fm cross n over F will be Mn. So that is some basic things which are present in example 17. And if V is a vector space over F, the zero subspace of V will be spanned by the vector 0. But we know that the set 0 is a linearly dependent set. So we cannot say that it is a basis, because a base should be a linearly independent set which spans. So we agree that the zero space is having the dimension 0, and sometimes we can say that the in an axiomatic way that the empty set is a basis for the zero subspace. So that means the empty set spans set 0, as the intersection of all subspaces containing the empty set is set 0. So the empty set is linearly independent, as it doesn't contain any vectors. So that is some concepts we get from there. Then we move on to lemma. The statement of the lemma says let S be a linearly independent subset of a vector space V. Suppose beta is a vector in V which is not in the subspace spanned by S, then the set obtained by adjoining beta to S is linearly independent. To prove that, we are taking this S in the hypothesis, and it is said to be a linearly independent subset of V. So definitely we are taking distinct vectors alpha 1 etc alpha m, which are linearly independent in S. Okay. And then what we do is we are going to adjoin a beta along with this S, right? Which is not in the subspace spanned by S. And we have to prove that the set obtained by adjoining beta to S is linearly independent. So for that, we are assuming this statement. We are assuming that C1 alpha 1 plus etc plus Cm alpha m plus B into beta is equal to 0. We have to prove that C1 is equal to 0, C2 is equal to 0, etc. Cm is equal to 0, B is equal to 0. That is our aim. So we claim that B is equal to 0. How to prove? Proof of claim. For otherwise, beta not equal to 0 will imply we can, B not equal to 0 will imply we can divide the whole of this by B. So you get C1 by B alpha 1 plus etc plus Cm by B into alpha m plus beta is equal to 0. That will imply beta is equal to minus C1 by B into alpha 1 plus etc. plus minus Cm by B into alpha m. And that means that beta is the linear combination of alpha 1 etc. alpha m. That means it is in the subspace spanned by S, which is a contradiction because we had in the hypothesis mentioned that beta is a vector in V which is not in the subspace spanned by S. So you have a contradiction there. So our claim is proved, which says that B is equal to 0. So this equation can be rewritten as C1 alpha 1 plus etc. plus Cm alpha m is equal to 0. And we already know that S is a linearly independent set. So if we assume like this, we know that C1 is equal to 0, C2 is equal to 0, etc. Cm is equal to 0, and we have already obtained that B is equal to 0. So that gives us the statement which is to be proved. That means the set obtained by adjoining beta to S is linearly independent. So we are done there. Now theorem 5 has the statement: if W is a subspace of a finite dimensional vector space V, every linearly independent subset of W is finite and is part of a finite basis for W. So whenever you have a finite dimensional vector space V and W is a subspace, each linearly independent subset of W will be finite, and they are a part of a finite basis for W. For that, suppose S naught is a linearly independent subset of W. Okay, so what we have to prove? We have to prove that the set we are talking about is finite and it can be extended to a basis for W. So if S is a linearly independent subset of W containing S naught, then S is also a linearly independent subset of V, right? Why? Because here S naught is a linearly independent subset of W. S is a linearly independent subset of W containing S naught. Then whenever S is a linearly independent subset of W, it is also a linearly independent subset of V because W is a subset of V. So that's obvious. Now as we are given that V is finite dimension. So the S we have now talked about will contain maximum the dimension of V elements. Dimension of V, number of elements, right? So now we are going to extend this S naught we first mentioned to a basis for W by the following procedure. Suppose if S naught spans W, S naught is already linearly independent, that means S naught is a basis for W. So we are done because it is a part of finite basis for W. Suppose if it is not, that means S naught is not spanning W. By the earlier argument of the lemma, we are able to find a vector beta 1 in W and incorporate it with this S naught such that the new set S1 is equal to S naught union set beta 1 is independent. We can do like that. Now, if S1 spans W, we are done. If not, we will be able to find a vector beta 2 and incorporate it with this new set S1, and we call S2 is equal to S1 union set beta 2 such that it is linearly independent, and we continue the same likewise. We know that we have to continue it only up till dimension of V number of steps. So we know that we will reach such a end. So that set will be Sm is equal to S naught union set beta 1 etc. beta m, and then automatically that will be a basis for W because we can move only till dimension of V number of steps. So we are done there. Now corollary 1 gives a statement: if W is a proper subspace of a finite dimensional vector space V, then W is finite dimensional as well as dimension of W is less than, strictly less than dimension of V. This is also a very important result. We may assume that this W contains a non-zero vector. Why? Because it is a proper subspace from the hypothesis. By the earlier theorem, theorem 5, as we moved in the proof, we know that there exists a basis of W containing this alpha which contains at most dimension of V number of elements. That is true. So the maximum possible value of dimension of W will be less than or equal to dimension of V definitely. Now we know that W is a proper subspace. So definitely there is a vector beta inside V which is not in W because W is proper. Adjoin that with any basis of W, we will definitely obtain a linearly independent subset according to the logic we just discussed in the earlier proofs. Now, so that will mean you can remove the equality sign there. So definitely you get dimension W is strictly less than dimension. Corollary 2 says that in a finite dimensional vector space V, every non-empty linearly independent set of vectors is part of a basis. That follows from these earlier statements. Corollary 3 is an important statement. Suppose if A is an n by n matrix over field F, and suppose the row vectors of A form a linearly independent set of vectors in Fn, then A is invertible. We have to show that A is an invertible matrix if the hypothesis like this. So for that, we are going to consider the row vectors of A, and we are calling the rows as alpha 1, alpha 2, etc. alpha n. There are n rows because A is an n by matrix. Now suppose W is the space, you have n of them. We are going to take the span of them. They'll take the linear combination of all of these n row vectors. So suppose if W is a subspace of Fn spanned by this alpha 1, alpha 2, etc. alpha n. Now we know that we are given that alpha 1, alpha 2, etc. alpha n are linearly independent. So that means the dimension of W, already it is a subspace of Fn. We know that Fn over F has dimension n, and here this W is having n linearly independent vectors. So that has to be the dimension of W, which is n. Okay, so you have a subspace which has the dimension n and the vector space has dimension n. That will mean that the subspace is nothing but the whole space. So you get W is equal to Fn. Now what we obtain is we know that Fn over F has the standard basis which are the vectors epsilon 1, epsilon 2, etc. epsilon n, which is nothing but the n tuples having the first entry as 1, then the second entry is as 1, and rest of them are zeros like that. So since these alpha 1, alpha 2, etc. alpha n is also a basis, each of these elements in the basis of uh, standard basis, that means they can be written as a linear combination of these alpha 1, alpha 2, etc. alpha n. That is epsilon 1 is equal to some constant b11 into alpha 1 plus some constant b12 into alpha 2 plus etc. plus some constant b1n into alpha n, and so on in the same logic with epsilon 2, etc. epsilon n. And this is written as a general form like this. So every standard basis of Fn is written as a linear combination of these alpha 1, etc. alpha n. And from this logic, we can say that here this will be epsilon 1, this row will be epsilon 1, this row will be epsilon 2, etc. epsilon n. That is equal to the vector epsilon 1, epsilon 2, etc. epsilon n. And we know that this is nothing but in cross n, the identity matrix. That is equal to the coefficients coming here, okay, into alpha 1, alpha 2, etc., alpha n. And we know that this is nothing but I is equal to BA. So you get that A has an inverse B. So you conclude there that A is invertible. Now goes the important theorem, which is theorem 6, which gives us the statement if W1 and W2 are finite dimensional subspaces of a vector space, then W1 plus W2 is finite dimensional and dimension of W1 plus dimension of W2 is equal to dimension of W1 intersection W2 plus dimension of W1 plus W2. We have W1 and W2 are finite dimensional vector spaces. Definitely W1 intersection W2 is a vector space. It's a subspace of V. You can check it out. And since it is a subspace of W1 and W2, both being finite dimensional, this W1 intersection W2 is also a finite dimensional space. So it has a finite basis. Call it set alpha 1, etc., alpha k. Okay, since W1 intersection W2 is a subspace of W1, this basis can be extended along with some other elements so that the set of these elements is a basis for W1. And similarly, since the basis set alpha 1, etc., alpha k is a basis of W1 intersection W2 and it is a W1 intersection W2 is a subspace of W2, this basis can be extended along with some other extra terms together such that the whole set here is a basis for W2. And definitely W1 plus W2 will be spanned by the vectors alpha 1, etc., alpha k, beta 1, etc., beta m, and gamma 1, etc., gamma n. Now we claim that these vectors form an independent set. That means the third set. Okay, proof of claim. So for that, we are taking all the linear combination of the three sets with some constants and equating them to 0. We have to show that each of the constants is equal to 0. That is xi is equal to 0, yj is equal to 0 and z are equal to 0. So from this you get minus summation z r gamma r is equal to summation xi alpha I plus summation yj beta j, which shows that summation, this means that the summation Z r gamma r minus is a linear combination of alpha i's and beta j's. So from this you know that that means uh, the term sitting here is belonging to W1. Fine. And already we know that summation Z r gamma r will belong to W2 because that is this gamma 1, etc., gamma n are coming inside W2. So definitely that is belonging to W2. So since it is belonging to W2, we know that it is also belonging to W1 and it is also belonging to W2. So that means that element can be written as a linear combination of alpha 1, etc., alpha k because it is belonging to both of them, right? Um, what is the logic there? Since summation Z r gamma r belongs to W1 intersection W2. So alpha 1, etc. Alpha k is the set of elements inside the basis of W1 intersection W2. So you can write like that for scalars C1, etc., Ck. Now we know that the set alpha 1, etc., alpha k, comma gamma 1, etc., gamma n is linearly independent. So that will mean that the said r's will be 0. So you can rewrite this equation to be equal to summation xi alpha I plus summation yj beta j is equal to 0. And since alpha i's and beta j's together is also a linearly independent set, you get xi's are 0 and yj's are 0. That means in total you get all these coefficients xi, yj, zr, all of them are zeros. That means the set sitting here, the three of them together is a basis for this W1 plus W2. So finally you get dimension of W1 plus dimension of W2 is nothing but K plus M. That's how we moved through the proof. Through the proof. So you get K plus M plus K plus N, that is equal to K plus M plus K plus N, which is nothing but dimension of W1 intersection W2 plus dimension of W1 plus W2. And you can read through the some among the observations in the last section, last paragraphs, and solve out the exercises which are coming after this section. Thank you for watching. See you in the next video lecture.